for over the time period. So probably in first year it may be I1, then I2 in the second year, I3 in the third year. So this kind of a models where we are trying to compute the accumulated value, probably the expected accumulated values, as well as the variation in the accumulated value, variance or standard deviation in the accumulated values, because the interest rates are not assumed to be constant for the entire period. They are assumed to be volatile during the period. So that is where we are calling them as stochastic varying interest rate model. So whenever we are talking about this varying interest rate, as I said, I am expecting that our interest rate is changing from year to year. But one more major assumption that is taken is, yes, they are changing, but they are changing independently. So probably the interest rate of year 2 is not dependent anyway on the interest rate of year 1. When we are talking about that kind of a mechanism, so based on these interest rates, I will compute the expected value of the interest rates. So which is the average or a weighted average. Expected value of the interest rates is taken. So which is generally called as some J, the expected value of interest rate. So this is the mean interest rate. Similarly, we are talking about the variation in the interest rates. We can find out the variance of the interest rates S squared. So based on these two numbers, once the individual interest rates for each of the periods are known, we can compute the expected value of the interest rates J, which is nothing but the expected value of the individual interest rates. Similarly, we can find out S squared, which is the variance of the interest rates, by going with directly computing variance as nothing but expected value of x squared minus expected value of x whole squared. Using this phenomenon, you find out the variance of the interest rate, and square root of that will give you the standard deviation of the interest rates. Now, based on these two, if I want my accumulated value after n periods, so a simple expected value of this accumulation is nothing but 1 plus j to the power n, which is the expected interest rate, to the power n will be the expected value of the accumulation. Whereas if I want to find out the variance of the accumulated amount, it's better that you go with 1 plus j squared plus s squared, take it to the power n, minus 1 plus j to the power 2n. This is especially a formula which you can use, especially if you want to find out the variance in the accumulated value after n years. So probably the expected value is this much. Variance is coming out as 1 plus j squared plus s squared to the power n minus 1 plus j to the power 2n. So simple logic, right? So if at all I want to know what is happening there, I could have taken expected value of so because the variance for me is nothing but, see, if I have to look at it, the variance, as I said, is expected value of x squared minus expected value of x whole squared. So expected value of x is something which we have already got, which we have got as 1 plus j to the power n is the expected value of. So probably here, to make it even more simple, variance of Sn is nothing but expected value of Sn squared minus expected value of Sn whole squared. So expected value of Sn, which we have already found out, 1 plus j to the power n. So that I am taking whole squared. So the second term is directly coming out as 1 plus j to the power 2n in our formula. Now expected value of Sn squared, if I want, it is nothing but expected value of 1 plus each I squared. 1 plus I1, I2, I3, 1 plus I1, 1 plus I1 squared, 1 plus I2 squared. So the summation of all of them. So basically I could have written it as expected value of 1 plus 2I plus I squared. So expected value of 1 is 1. Expected value of 2I. 2 into expected value of I, which is j. So expected value of I squared, right? Expected value of I squared, I could have written it as variance of I plus expected value of I whole squared, because variance of I is nothing but expected value of I squared minus expected value of I whole squared. So expected value of I squared, I could have written it as variance of I plus expected value of I whole squared. So this is becoming 1 plus 2j plus j squared plus variance of I. So which is nothing but 1 plus j squared plus variance of I, we have taken it as s squared. So obviously this is coming out as 1 plus j squared plus s squared to the power n minus 1 plus j to the power 2n. So this is what is coming out to be the variance of my accumulated value. So one kind of situation which we would see here is, given the interest rates are volatile, given the interest rates are variable year over year, I will end up finding out the expected value of the interest rates. I will end up finding out the variance of the interest rates, and based on the, once I have found out J, which is the expected value of the interest rates, S squared, which is the variance of the interest rates, I can use both of them to find out the volatility, the expected value of Sn as well as the variance of my Sn. So that is one set of mechanism which I can use to compute the accumulated values and their volatilities, especially if the interest rates are not constant across the period. The other set of mechanism that is being discussed is, what if the interest rates follow a distribution? Another set of questions which we generally observe is, okay, the interest rates are expected to follow a distribution. Instead of saying these are the interest rates for different periods, I am trying to see that the different interest rates are following a distribution. For example, 1 plus I is expected to follow a log normal distribution, right? So probably a log normal distribution will have mu and sigma squared as the parameters for it. Similar, if that is the case, 1 plus I to the power n, which is nothing but Sn. Sn then is again assumed that it will follow a log normal distribution itself with n mu and n sigma squared as the parameters. Right. So if Sn is following a log normal distribution, as per the property we can say logarithm of Sn will follow a normal distribution with again n mu and n sigma squared as the parameters. And so from here probably we can say that the z, right, when we are talking about the probability of some, see probably log Sn is following a normal distribution with this, means x minus mu by sigma log Sn minus n mu by square root of n sigma squared. This is following a normal distribution with 0 and 1, means this is actually a kind of a z value that needs to be found out for typically finding out probability of Sn greater than or equal to some x, or probability of Sn less than or equal to some x. To find out some such kind of stuff, we can very well use, especially if someone is saying 1 plus I will follow a log normal distribution with some mu and some variance, we can very well say Sn is following 1 plus Sn is nothing but 1 plus I to the power n. This will follow a log normal distribution with parameters n mu and n sigma squared. So logarithm, so the definition of the log normal distribution is nothing but the logarithm of Sn will follow a normal distribution, but to make it standard normal distribution, I'll subtract x minus mean divided by the standard deviation. So that is giving me that x minus mu by sigma is following a normal distribution with the mean 0, variance 1. So from here I can very well find out the probability of Sn less than something or greater than something by finding out this z value and trying to map this z value against a z table, trying to find out the probability of the value lesser than that or greater than that kind of scenarios. But sometimes what could happen is, for the interest rates, see, we also know, if at all we don't have these values, we also know that if 1 plus I is following a log normal distribution, then the expected value of the 1 plus I can be obtained as e power mu plus half sigma squared, and similarly the variance of 1 plus I can be obtained as e power 2 mu plus sigma squared.